Welcome to my video on multilayer perceptrons. These are probably the most common type of artificial neural network and the best understood type. All neural networks are built up of a large number of simple units, connected together in some way so that they can pass signals from one unit to another. This mimics the human brain, which consists of countless simple units, called neurons, connected together so that they can pass signals from one neuron to another. Except that neurons aren't simple at all. We only know vaguely how signals percolate through neurons and networks of neurons. There are, in fact, no fewer than 45 different types of neuron in the human brain that we know about, and we don't have perfect mathematical models of any of them. Here, however, is a general overall picture. The body of the neuron is called the soma. Signals enter the neurons through several different input connections called dendrites. These signals build up in the soma until some sort of threshold is reached, whereupon the neuron discharges through a long output connection called the axon, passing an output signal to other neurons via their dendrites. We often think of neurons passing electrical signals to each other and building up some sort of electrical charge. However, the signals take the form of chemical ions that pass across the tiny gaps between axons and dendrites. These gaps are called synapses, and the patterns of information stored in these collections of neurons is stored in the strengths of these synaptic connections. And from these vast networks of neurons, with their connections, arises each and every human faculty: memory, imagination, emotions, logical thinking, and of course, consciousness. And how that happens, we haven't the faintest idea. So, if we don't have an exact mathematical model of a neuron, what do we use? Again, there are different algorithms for simulating neurons in the computer, and different researchers have their favorites. However, they tend to boil down to something like this. The soma is that circular thing in the middle, with a series of input connections representing the dendrites. Each input connection has a strength associated with it, often called weight, so that it receives a greater or lesser proportion of the input signal connected to it. Neurons can take in input from an external source, which could be something like a camera or other sensing device, or could just be some sort of input on the computer, in other words, a piece of data, or from the output of another neuron. The signal coming into the neuron is therefore the weighted sum of all the inputs. Take each input, multiply it by the weight associated with it, and tot up the result. Whereas a real neuron will gradually build up chemical signals within them, a simulated one generally passes on the signal straight away to its output, which is connected either to the input of another neuron or provides the output of the neural network itself. However, first of all, the signal has to pass through a transfer function. This is a transfer function that determines what the neuron does with the signal. Here are some examples of transfer functions. The x-axis of the graphs represents the weight sum of the input signals. And yes, it's perfectly possible for that weighted sum to be negative. Some of the weights on the input connections might well turn out to be negative, thereby reducing the total input. You'll notice that the output of the neurons is typically limited to the range 0 to 1, with 0 indicating that the cell didn't fire, and 1 indicating that it fired to the greatest extent. The simplest function is the first, a step threshold. If the total input fails to reach the threshold value, there is no output, or rather, the output is 0. A slightly different version allows the neuron to produce a scale response, so that below a certain input value, it produces nothing, and above the threshold, it is limited to the maximum value, but between those values, it returns a proportion of the input signal. These were called linear thresholds. The earliest example of an attempt to construct a network of artificial neurons was carried out by Waller McCulloch and Walter Pitts in 1943. They used neurons which were little more than the sort of digital logic gates you might see in an electronic circuit. More researchers started becoming interested in them in the 1960s, and it looked as though neural network research had a bright future. That was until a book was published that killed the field stone dead for a good few years. More on that later. The neural networks generally used then connected the inputs of the neurons directly to the input of the program, and the outputs provided the output signal. They generally used either simple step thresholds or linear thresholds. The term perceptrons was coined for such networks. The idea of the perceptron was first developed by Frank Rosenblatt in 1958 in his paper The Perceptron, a Perceiving and Recognizing Automaton. Take a look at this perceptron, consisting of one neuron with two inputs, which I've termed X and Y. We want the neuron to produce an output of 1 if Y is bigger than X, or 0 out otherwise. We can draw an XY graph with a diagonal line on it, equation Y equals X. Y is bigger than X for every point above that line, and smaller than X for every point below it. And I have marked the two regions blue and red respectively. We call this situation a linearly separable one, as the two regions can be separated by a single straight line. As you can see, the setup for this problem is trivially easy. Just set the weight on the X connection to -1 and the weight on the Y connection to 1, so that the weighted sum is Y minus X. If the threshold on the neuron is at 0, then the neuron produces a 1 if Y is bigger than X, 0 otherwise. Here's an example of a linearly inseparable problem. This time we have a neuron that must produce a 1 output if X and Y are of different signs, i.e. Y is positive and X negative, or vice versa. This is sometimes called the exclusive OR problem, and it is linearly inseparable because you can't draw a single straight line on that graph that separates the blue region from the red one. Research into perceptrons and connectionist AI in general suffered a great blow when researchers Marvin Minsky and Seymour Papert published their famous book titled Perceptrons, An Introduction to Computational Geometry in 1969. They pointed out that a simple perceptron cannot distinguish between inputs in a linearly inseparable problem. They went on to prove mathematically that this also applied even if you had several layers of perceptrons, with the outputs of one layer feeding the inputs of the next. The transfer functions of all these early perceptrons were linear, i.e. had equations that basically described straight lines. It can be shown that feeding processed signals from one perceptron to another, and then another, in different layers makes no difference. Effectively, all those different perceptrons in the chain could be replaced by one single one, with weights and transfer function calculated appropriately. However complicated you made the layers of perceptrons, you still wouldn't be able to solve any linearly inseparable problem. Effectively, this meant that perceptrons could not cope with any problem more complicated than the simplest ones. The book is significant because it caused research into neural networks to grind to a halt for well over a decade. Some people refer to this as the period of the AI winter, when research was directed just about entirely towards symbolic AI, an approach which has largely petered out in recent years. There was much resentment to Minsky and Papert, to the point where they had to produce a new edition of the book in 1980, with the criticisms addressed in a new chapter. However, there was nothing wrong with their maths. Anyway, for good or ill, research into neural networks just about dried up for several years. It was only revived because of two ideas. Firstly, it was discovered that the objections that Minsky and Papert raised could be addressed by making the transfer a non-linear one. Behold the sigmoid transfer function. The inputs are adjusted by their individual weights, and a threshold for the perceptron is subtracted. The resulting figure is passed through the non-linear sigmoid transfer function to produce the output for the perceptron. The equation for the sigmoid function is based on an exponential and never gives a value of exactly 0 or exactly 1. For very small inputs, i.e. very negative for want of a better phrase, it produces an output value of almost 0. For very large inputs, very positive, it produces an output that is almost 1. For a total input of exactly 0, it produces 0.5. The key word there is nonlinear. A nonlinear transfer function for each perceptron means that a perceptron feeding another perceptron, which feeds another perceptron in turn, can't simply be collapsed into a single layer using mathematics. The nonlinear transfer functions are the secret to getting the perceptrons to cope with linearly inseparable problems. Minsky and Papert have been overcome. Effectively, a well-trained perceptron with several layers, a multi-layer perceptron, could cope with any classification task. However, this led to another problem. How should we go about deciding what the weights and threshold for each perceptron should be? This is where the other great idea came in, the formulation of the back propagation algorithm. But that's a story for another lecture. So where are we now? Well, here's how a fully fledged multi-layer perceptron actually works. Here you have one with 8 inputs on the left and 2 outputs on the right. Traditionally, these diagrams are always shown with a signal traveling from left to right through the MLP. You'll notice that the outputs of the perceptrons in the earlier level, close to the inputs on the left, are connected to the inputs of more than one perceptron in the layer next to it. Usually, each perceptron takes its input from all the perceptrons in the layer to its left, or from all the inputs if it's in the first layer. Typically, we want the MLP to distinguish between different patterns and produce a different output depending on what pattern was presented at the inputs. For an MLP like this, we would train it to distinguish between two different input patterns, referred to as training patterns. For one of those input patterns, it would produce a high output, a 1, on the top output, and a low output, a 0, on the bottom one. For the other training pattern, it would produce a 0 on the top output and a 1 on the bottom. We'll assume that the weights and thresholds of the perceptrons have been set up correctly. You present one of the input patterns at the input and allow the signal to percolate through the MLP. With each neuron, I'll call them neurons from now on, neurons, nodes, perceptrons, I tend to use the terms interchangeably. With each neuron taking input from those in the layer on the left, or the inputs, and providing output to the neurons on the right, or the outputs themselves, of course. Providing the weights have indeed been set up properly, the appropriate output will go high. Now you present a pattern which isn't one of the input patterns. After the MLP has done its stuff, there isn't a clean 1-0 output. One of the outputs will be higher than the other one, and whichever output is higher indicates which training pattern the MLP thinks is most similar to the one actually presented. This is the strength of multilayer perceptrons, the fact that you can train them on examples of patterns, after which they can classify patterns that are similar to the training ones, but don't have to be identical to them. In the next lecture, I'll be explaining how the backpropagation algorithm works, and you'll find out how those neurons can be trained to do something useful. Goodbye.